So today we have discussed basically the lower mass limit of a star. Now the idea not only happens to star but everywhere. Say for humans, when a child is born, you will hear doctors saying that if the weight of the child does not exceed 3 kg or say 2.5 kg within 1 week of its birth, the child will not be able to live. So this means that there is a minimum criteria even for humans, and we are talking about stellar object stars. So to give you a rough idea first about how to estimate the lower limit of stars. So what we have to do is we have to consider this log density, log temperature plot. That means, what is this? This is basically the equation of state regimes we have to consider. Now, all these cases we have already covered in our previous classes. We have covered what will happen to the case for ideal gas. There we have incorporated the idea for the ion pressure and electron pressure in ideal gas using the mean molecular weight concept, right? Then what will happen to the photons? You see, in the star we not only have ions, not only have electrons, we also have neutral atoms, also photons, all of them we have. So what will happen to the photon? That is radiation pressure. We also know P is equal to 1 by 3 8 to the power 4, and here we have similar ideal gas law, that is P proportional to N kBT. Also, when the self-gravitating system collapses, right, what will happen is that when the collapse is so large that atoms come close to each other, they get squeezed to each other, then because of this pressure ionization, electrons will be freed, and what will happen is that degeneracy may start becoming important, which is the quantum effect. That means the de Broglie wavelength of the atom will become, even the electron, de Broglie wavelength will become close to the order, will become close to the interatomic distance, right? So de Broglie wavelength of the atomic system becomes equal to the interatom separation during pressure ionization also, and then our ideal gas law will not be valid because we will have to talk about Fermi distribution, not the Maxwell-Boltzmann distribution from where we get the ideal gas law, right? So we will have degenerate matter in that case. Now again, we have already worked this out in our class. So we have worked out the case for degenerate matter, and while doing the entire mathematics we assume T is equal to 0 case, right? T is equal to 0, and for that entire expression we found the expression for pressure and also the energy density. Remember, Fx and Gs functions were there, and from there we calculated two particular cases. One is non-relativistic case, which happens at low density, and another is ultra relativistic case, which happens at higher density. So this we have already done. Now what we want to investigate in this particular class is the lower mass limit of star. Okay, so basically we are talking about a star, that means basically we are talking no star right now. What I want to say, lower mass limit of a star. Now what is a star? We already talked about. What is a star is, now two criteria has to be fulfilled. Number one, a star means it is a self-gravitating system bound by gravity. Second criteria, and that is when there must be fusion inside. Now when does fusion happen? When during the gravitational collapse, the density increases, slowly the pressure inside will increase, and as a result the temperature increases. Now as the temperature increases, what happens is that the thermal energy is increasing, so the nuclei, they can come close to each other. Okay, when they come close to each other, then through quantum mechanical tunneling, we can have fusion reactions. Okay, so what is important is increasing temperature so that the fusion can happen. At least the proton-proton chain reaction can initiate. Then only we can call that self-gravitating system a star. So what we will have to do to find the lower mass limit of a star is to find the condition for the central temperature. Okay, what it should be very high. The central temperature should be very high. And what I would like to know is what is the mass when the central temperature reaches the proton-proton chain reaction. It can initiate like that. Now, for that, look into this diagram. This is the temperature, this is the density logarithmic. Now, this is the ideal gas part. Okay, and we know that here the equation of state, that means pressure, it depends on density, temperature, and also the composition. Okay, sometimes we don't write it, but composition is always there. And that is incorporated using the mid-molecular weight concept, right? Now, what can happen is that, suppose the self-gravitating system is slowly collapsing. So what is happening? Suppose our self-gravitating system is somewhere over here. Let me talk in terms of the density temperature plot. What we want is a very high temperature so that proton-proton fusion reaction can initiate. So slowly the temperature is increasing. However, after some time, this gas, it crosses this line. What is this? That means it reaches this region, which is the non-relativistic degenerate matter region. What will happen? At that moment, its equation of state will change. And you know, for degenerate matter, the equation of state is pressure depends only on density. That means no temperature dependence. Then what will happen? As soon as this self-gravitating matter, its pressure increases and it enters this region, the temperature dependence will vanish. What this means is that even then the pressure will keep on increasing, the density will keep on increasing, but temperature will not increase. And so no fusion will happen. So this means that the criteria for lower mass limit of star, it must be that we must never reach the degeneracy region, non-relativistic degeneracy region. And for self-gravitating systems where such thing happens, we call them by different name brown dwarf. What do we call them? Brown dwarf. Okay, so this is the name. We call them brown dwarf because in that gravitating system there is no initiation of fusion reaction because of decoupling between pressure and temperature. So even though that density keeps on increasing, temperature will not increase and no fusion will happen. Okay? Any questions? This is very basic idea. So what we are going to do is we are going to investigate this idea. Okay? So let's see. So here I have shown you the first method. So this is the first method, this is the second method. So we have got two methods. I have demonstrated over here. Now let's see what happens. Here I have shown you what is the kinetic energy of the electron. Half me v square, right? Now this is also equal to 3 by 2 kBTC. If you equate that, then from there you can get momentum relation and ultimately your de Broglie wavelength. Now suppose the core has equal protons and electrons and the mean separation between protons be the L. Then what you can write is, you can write rho c is equal to mp by L cube. Okay, very basic. And from there you get an idea about the mean separation, an expression in terms of central density. Look, remember, fusion, if it occurs, it will happen where the temperature is high. And where is temperature is high? In the very central part, where the density is very high. That means the particles can come very close to each other. Okay. So I am talking about central. That means small r is equal to 0 case only. Here. Fine. So I am getting an expression for L. I am also getting an expression for de Broglie wavelength. Right. Now, what I want for no electron degeneracy is that this interatomic distance, it must be greater than your de Broglie wavelength. So we get an inequality, and that I have restated in terms of the central density. This inequality, very basic algebra, nothing else. Now next, you see here what we have is central density and central temperature, but no mass. What we want is a relation inequality for mass. How do we do that? If you remember, I just talked about previously that in stellar theory, just sitting in the classroom, there are two ways of estimating the temperature of a star. One is using hydrostatic equilibrium, another one is using your virial theorem. Now let me here see how to exploit this relation. Now this I have already previously discussed in the class. So we will be using the virial theorem to find an average temperature known as virial temperature of the star. And this expression is like this. This I have already covered previously. Okay. So this is your virial temperature. Now if I use this inequality here, you see we have got rho c and Tc, but here I have just got an average value from this virial temperature expression, T virial and rho average. Remember the dependence, m to the capital M to the power 2 by 3 mass, and density rho to the power rho average to the power 1 by 3. Now what I do this time is I use an approximation that suppose the central temperature is 10 times the virial temperature and the central density is 100 times the average density. This is just an approximation. Let's see what we get from there. And also I use the mean weight 0.6 value. Then from there, if I use this and incorporate in this inequality, you can check by yourself. This is little bit algebra. You will get this inequality. M is greater than M minimum, while M minimum is given by this relation. This is power 4 by 3. Okay. So this is your minimum mass estimation. Now let's see the experimental value. If I do put in the values for the proton-proton chain over here, then you will see that the minimum mass comes around 0.1 solar mass. So this is actually really observed. The experimental values, the actual stellar modeling when people do, they use even more sophisticated stuff, and the actual limit for brown dwarf is 0.08. You must remember. So mass of brown dwarf is of the order of 0.08 solar mass. So this is the actual limit. But even using this very simple idea, so what we have used? We have used the condition for degeneracy, basically the interatomic distance and the de Broglie wavelength. Next, we incorporated our virial theorem and found virial temperature. Then number 3 point is we use this approximation, this set of approximation. So using these 3, we still get a very good idea about the minimum mass of star, which is 0.1 solar mass. So this is the first method. Now let me talk about the second method. Now here you remember we talked about the various models for stars. Now the most simple model is the constant density model. That means the throughout density is constant. Come on, this is just not possible, because in the central part the density is much higher. But if you do that, you will again get a value of pressure as a function of R just using two equations. One is equation of continuity, another is equation of hydrostatic equilibrium. Here I have used a much more sophisticated model. This is known as quadratic density model. Quadratic density model. Okay. So here you see the dependence is like this. rho r is equal to rho c into 1 minus small r square by capital R square, where capital R is the radius, okay, of the self-gravitating system. Now, after using the continuity equation, you will get this relation. Again, I am asking you to check these relations. So, from here you see, we get rho c as a function of the total mass. Next, I am going to use the hydrostatic equilibrium. dpdm, not dpdr, dpdm. From there, you see, I get this central pressure as a function of, again, total mass m and total and the radius r. From here, I am getting this. Next, I have to incorporate the temperature, and for that I have to use a form of, I have to use an equation of state form, right? So I am assuming ideal gas law. So I am assuming ideal gas is there inside, and from there I will get my familiar ideal gas law. And if I incorporate all these two results here, then you see I get this relation, where I am getting a relation between Tc and rho c. This is very similar to what we have previously here. Here we have virial and average density, and here we have Tc and rho c, just because of using a different model. Okay, there you see the model itself was incorporated, was given by your virial theorem. This was the model. Basically, virial theorem gave you the result in itself. So we got this using the virial theorem. But here, this dependence is given by this particular density form. Now, what do we need for no electron degeneracy is that this pressure must be greater than this, or this means that we must remain in this region. We should not go over there. And from there, you see, gas pressure is just this ideal gas pressure, and this I have already worked out previously. Non-relativistic pressure, so it is equal to K1 or K non-relativistic into the dependence is rho c by mu to the power 5 by 3. Okay, and so if you do that, so again you get this relationship using these values, and if you put in the various constants, you get this value. And for PP chain, the value is like this. M is greater than 10 to the power 30. But remember, the solar mass is 2 into 10 to the power 30. So this means this model is giving me a very large value. Okay, roughly 10 times more the value of the experimentally observed. But still, I am getting something which I can readily calculate. Okay, the value can be small, the value can be big, but the important thing is that I am getting an idea from very basic principles of physics how to estimate the lower mass of a star. Any questions? Bolo. Next, maybe in the next class, I will talk about the upper limit of star, upper mass limit. And there, this time you see, we investigated this region, right? We investigated this region. For the ideal gas, over here, there are two regions. One is over this side, another is this side. Now, what is there? We have radiation. That means, and you already know from Virial theorem that for a gas of classical relativistic particles, the total energy E total is equal to 0. What does this mean? Suppose we have a gas, a self-gravitating system entirely of gas particles, and there I just put in a torchlight. So I am just doing a small perturbation, sort of putting in some photons. Since the energy is already 0, it will just disrupt. Unbound. It will just become unbound. Right. So this means that the upper mass limit will be given by this region when this gas pressure becomes equal to the radiation pressure. Okay, this we will investigate in the next class.